Evaporation is a word for the physical change from a liquid to a gas. So when something changes from a liquid to a gas, we say it evaporates or it's vaporized. Two different words for the same thing. Now, the rate at which something vaporizes is going to depend on the surface area, the temperature, and the strength of the intermolecular forces. Let's think about water. If we want water to evaporate, let's say we just washed our hands after using the bathroom and our hands are wet and we want them to be dry. Well, one of the things you can do is go to the hand dryer, right? What does the hand dryer do? It blows warm air on your hands. When you increase the temperature of the water, more of the molecules have enough energy to get into the gas state, and so they will evaporate faster. Do you stand there under the dryer with your hands just standing there waiting? And what do? You rub them together, right? What that does is it spreads the water out and increases the surface area. Only the molecules at the surface can evaporate. If the surface area is greater, the water will evaporate faster. If you take a glass of water and set it on the counter and take the same size glass of water and spill it on the floor and just wait for it to evaporate, the water on the floor is going to make a large puddle with a large surface area. But probably by tomorrow morning it'll all be gone. It'll have evaporated. The cup of water on the counter is still going to be there. It might be a little lower, but it's got much lower surface area, and so it's going to evaporate more slowly. The other thing we can do is decrease the strength of the intermolecular forces. Well, you can't really change that in a liquid, but if you compare two liquids that have different intermolecular forces, the one with the weaker forces will evaporate faster. The word volatile refers to liquids that evaporate more quickly, and non-volatile refers to those that do not vaporize easily. So, like vegetable oil. Does the vegetable oil evaporate? If it does, it's really slow, right? But alcohol or gasoline evaporate very quickly. And so those are called volatile liquids. So let's look at water molecules in a beaker. Well, the water molecules on the top are not held as strongly as the ones in the interior because these guys are only held from the sides and the bottom, right? And so they're not being held as much. When we think about average kinetic energy, a beaker of water has an average kinetic energy that is proportional to its temperature, but it's an average. So there are some molecules that have high kinetic energy and some that have low kinetic energy. If you have molecules with high kinetic energy at the surface, they can just break loose. So here we have our red rover line at the surface of the water. If you have a particle that's running fast enough, it can break through the line. Because if you're running at the red rover line, you're much more likely to break through than if you're just strolling along. They're going to stop you if you're just walking. You have to run at the line to break loose. So it's the fast particles, the high energy particles are going to escape. So increasing the temperature increases the number of particles that have enough energy to break through. So increasing the temperature increases the rate of vaporization. Only molecules at the surface can get away. And so increasing the surface area means there are more molecules at the surface, and the rate of evaporation will increase. If the interactions here are very weak, it's first graders instead of the football players. Well, now you don't need as much energy to escape, to break through the line. And so at a low temperature, the rate of evaporation will be larger. Does that make sense? Oh, I got ahead of myself. So here's fraction of molecules with a given energy versus kinetic energy. At a low temperature, the average kinetic energy is lower than at a high temperature. But even more importantly is, as you increase the temperature, the distribution spreads out. This curve becomes broader. And so if we look at the area under these curves, this dotted line is the minimum energy needed to escape. And so for the cooler substance, it's just the particles under this line, the blue line, that have enough energy to get out. The red line, there's over twice as many particles that have enough energy to get out. So the rate of evaporation will be larger. Condensation is the opposite of evaporation. It's going from a gas state to a liquid state. If you have a situation where you have the rate of condensation and the rate of evaporation being equal, you have a dynamic equilibrium that is established. Does that sound familiar? We talked about that in chapter 15, so now this is going to make more sense than if we hadn't done chapter 15. So we get a dynamic equilibrium, and the number of gas water molecules above the liquid remains constant. That pressure that's exhibited by those gas particles is called the vapor pressure. It's the partial pressure of the vapor in equilibrium with the liquid. So let's look at a stoppered Erlenmeyer flask, and we've got some water in here. Initially, there's essentially nothing up here. There's just air. And in this climate, it's pretty dry air. So here we have water. What's going to happen is it's going to start evaporating, because that's what water does. At room temperature, water evaporates. The more energetic particles that get to the surface will go into the gas state. At this point, there's no condensation because there's no gas particles up here to condense. After evaporation has gone on for a while, now we have some water molecules that escaped into the gas state. And they do what gas molecules do. They go in straight lines until they bump into stuff, and eventually they're going to crash into the surface of the water and condense. When they splash down, they get trapped again. The rate of condensation is going to depend on how many molecules are here. If there's more molecules bouncing around up here, more of them are going to be hitting the surface. So as the concentration or pressure of the gas becomes larger, the rate of evaporation gets larger. The rate of evaporation, did I say that right? Condensation, the rate of condensation increases. The rate of evaporation isn't changing. That depends on the surface area, not changing. Depends on the temperature, not changing. Depends on the strength of the intermolecular forces. Well, it's still water, they're going to be the same. So the rate of evaporation is constant. But the rate of condensation increases as we get more and more water molecules in the gas state. At some point, the rate of condensation will equal the rate of evaporation. And then the amount of water molecules in the gas state will remain constant. It's dynamic, though. It's always changing. It's not the same water molecules all the time. There's some escaping and there's some condensing, kind of like a busy airport. You've got people arriving and you've got people departing. And if you looked at the population of the airport at 10 o'clock and at 11 o'clock, the number of people in the airport might be the same, but it's not the same people because they've been coming and going. That's the dynamic part of the equilibrium. But the rate at which the water molecules are leaving the liquid state comes to be equal to the rate at which they are entering the liquid state. Any gas exerts a pressure, and so these water molecules are going to emit a pressure, and that's called the vapor pressure. The vapor pressure depends only on the temperature of the water. At a higher temperature, what happens to the rate of evaporation? It increases. As the rate of evaporation increases, you get more and more gas, and eventually the condensation rate will be equal to it, but at that point you'll have more gas. More gas means more pressure. As the temperature goes up, the vapor pressure goes up. Any questions? I think this stuff is really neat, but you know, I'm a chemist, I'm kind of weird. So vapor pressure will increase if we increase the temperature. If you have a substance with weaker intermolecular forces, what does weakening the intermolecular forces do to the rate of evaporation? It increases it. So now we've got kindergartners in the Red Rover line versus the linebackers. Well, it's easier to get through. Rate of evaporation increases. That leads to more gas molecules, higher vapor pressure. The vapor pressure, though, is independent of surface area, because increasing the surface area does affect the rate of evaporation, but it also affects the rate of condensation. So if you increase the surface area, it doesn't matter, because it will affect both rates equally. The boiling point is a temperature at which a liquid boils. What does it mean when something boils, though? What happens when something boils is that the vapor pressure of the liquid is equal to the pressure above it. So you got a pot of water at 1 atmosphere, just sitting out in the room, 1 atmosphere of pressure. What happens to the vapor pressure of water as you increase the temperature? It goes up. Eventually you get to the point where the vapor pressure is 1 atmosphere. At that point, even molecules in the interior of the liquid have enough energy to escape into the gas state, and they will form bubbles. The bubbles go up and burst because they're less dense than the water. Forget what's coming next. Yeah, we'll stay with this one. Have you heard of a pressure cooker? What does a pressure cooker do? Why would you want to use a pressure cooker? Cooks faster. It cooks faster. Well, this explains why it cooks faster. In a pressure cooker, you have a lid on the pot that is clamped onto it. As you heat the water and more of it evaporates, that's going to cause pressure to build up in the pot, right? If the pressure above the water is greater than 1 atmosphere, what has to happen to the temperature before it starts to boil? It has to get higher. It won't boil until the vapor pressure equals the pressure above the liquid. And if you artificially increase that by putting a lid on it and clamping it on, then the water will boil at a higher temperature. If you take this pot of water up to Grant Grove, they've got snow up there. We were up there yesterday. It's beautiful. If you take it up there, the atmospheric pressure is less, and water will boil at a lower temperature. It'll seem to boil faster because when you put the pot on the stove and you start to heat it up, it won't take as long to boil. But the temperature of the boiling water will be lower than it would be down here in the valley. If you put it in a pressure cooker, the boiling point gets higher. One of the reasons that frying cooks faster than boiling is that oil you can heat to a higher temperature. I'll get back to my food analogies. I probably should have eaten lunch. Once you get to the boiling point of that liquid, additional heating will cause more rapid boiling. You'll see bigger, more violent bubbles coming up, but it's not going to change the temperature of the liquid. It's going to remain at the boiling point. what happens as you put more energy in is those high energy gas particles are escaping. They're taking off the high end of that distribution of kinetic energy. All the high energy particles are leaving, and that keeps the average the same. If you have, say, a country and you look at the per capita income, a measure of, how wealthy the country is, you've got some people that are really rich and some people that are really poor, right? But you have an average. Well, if all the rich people leave, what does that do to the per capita income of the country? It drops down. So when water is boiling, it's the high energy particles that leave, and the rest of them stay at that same temperature until they've all been converted to a gas. And then the gas can increase in temperature. So when you have boiling water, you're always going to have a temperature of 100 degrees Celsius at 1 atmosphere. After it's gone, after all the water's evaporated, then it will get hotter. So here we have this is called a heating curve. It's just kind of a misnomer because those look like straight lines to me. Those aren't curves. But if you look at the temperature of water versus the amount of heat that you've added to it. So here we're starting with water at 20 degrees Celsius, and we're going to add heat to it. The temperature is going to go up. Once it gets up to 100 degrees, it's going to start boiling, and the temperature will not go up until all the water has boiled away. So if you're cooking spaghetti, you boil the water, it's going to take the same amount of time to cook, whether you start it as soon as the water starts to boil, or whether you let the water boil for 10 minutes before you put the spaghetti in, because the temperature is the same. You can cook foods by frying them faster because the temperature of the oil can go above 100 degrees Celsius. A pressure cooker cooks food faster because it increases the boiling point of the water. Otherwise, no matter how big your fire is or how big your stove is, you're at 100 degrees Celsius with the water. So once all the water has been converted into the gas state, then the temperature can increase. Any questions? Cool thing my high school chemistry teacher did. I remember little snapshots of high school. And most of it's just this disturbing blur, right? But there's little things. And one of the things I remember is he took a really big filter flask and stoppered it. It had about this much water in the bottom of it. And he hooked it up to a vacuum pump. And he started the pump up, and it's going down and chug, chug, chug. And he's, explaining stuff to us. And after a while, the water starts to boil. And he made all of us come up there and put our hand on the flask. And the first person was, kind of scared, because who wants to touch boiling water? You're going to burn your hand, right? It's hot. It wasn't. He was evacuating the flask, reducing the pressure above the flask. Water boils when its vapor pressure equals the pressure above it. Vapor pressure of water is like 22 millimeters of mercury at room temperature. If you get the pressure in that flask down to 22 millimeters of mercury, the water boils at room temperature. It was the craziest thing. It's just, made a big impression, obviously. So there's energy involved in evaporation. Evaporation is endothermic. Pointer's not working. There we go. Endothermic. The system absorbs heat because energy is needed to break the molecules away from the liquid. Our bodies use the endothermic nature of evaporation to cool us off. We get sweaty when we're overheated, right? So you sweat and you get all wet. And if there's a breeze, the breeze comes and you're like, oh, that feels so good. It feels so cool. Because that's increasing the rate of evaporation of the water on your skin. As the water evaporates, it takes away the higher energy particles, and that cools you down. What's left becomes cooler. So if you have a breeze or a ceiling fan, that's going to increase the rate of evaporation, and the sweat will cool you off faster. If there's already a lot of water in the atmosphere, if it's a humid day, and you guys in the Central Valley, you have no idea what humid is. I grew up in Minnesota. I've lived in North Carolina. The day we got married, it was 95 degrees and 95% humidity. I mean, you could almost wring water out of the air. It was, nothing would evaporate because the air was already full. And you can sweat and sweat and sweat, and you do. And it doesn't do any good. It just rolls off of you and gets you all wet and smelly. High humidity will not, the air just is full of water already, and so that will reduce the rate of evaporation, and your sweating just doesn't do much good. Condensation is the opposite of evaporation, right? We talked about that. Evaporation is endothermic. This makes sense to us because if you want water to evaporate faster, you're going to put it on the stove and heat it up, right? You're going to put energy into it. Condensation, being the opposite, has to be exothermic. This doesn't make a lot of sense unless you start to think about it a little more deeply. When steam condenses on your skin, it can give you a very severe burn. Steam condensing, when it condenses, it releases a tremendous amount of energy. You can get much worse burns from steam than you can from boiling water. Think about your freezer. Okay, you put the ice cube tray with water into the freezer, and you come back hours later and you have ice cubes. How did it do that? It took heat out of the freezer compartment. That's what the compressor and the fan and everything in the back that's chugging away is doing. It's pulling heat out of the freezer. As something freezes, I got ahead of myself. I'm supposed to be talking about condensation. Now I'm talking about freezing. Okay, switch back. That's a hard switch to make. I like the freezing one better. Okay. Back to weather. We'll talk about weather again. So I grew up in the Midwest, and temperature fluctuations there are highs during the day to lows at night, sometimes only like 10 degrees. It was 85 during the day, and it gets down to all of 75 at night. The temperature just doesn't vary much within the course of a day. Here in the Central Valley, where it's generally very low humidity, it's not unusual to have a 40-degree temperature variation. It might be 65 at night and 105 at 3 o'clock in the afternoon, right? And so we never know what to wear, right? So we either just ignore it completely, and because regardless of how you dress, you're going to be right for part of the day, right? Or you dress in layers or sleeves that you can roll up and take your socks off and put your hair up, and you just vary things throughout the day. Why does the temperature not vary in a humid climate? And then it has to do with the moisture. And then think about those couple of weeks in the summer that it doesn't cool down. We went a summer without air conditioning. Yeah, it broke June 1st. Long story, we survived. But there's always, usually it cools down at night. You can open the windows, turn on the house fan, you're good. But there's always a couple weeks where it just doesn't cool down. It gets down to like maybe 75 or something, and you're like, this is just not okay. And it feels humid. And compared to what we're used to here, it is humid, but compared to Minnesota and North Carolina, not at all. But those are the times when the temperature doesn't drop, because the moisture in the air holds heat. And as it condenses, it releases that heat and keeps the air warm even though the sun has gone down. And so it moderates the temperature. The temperature at the coast is the variation is not very large, kind of like the Midwest. It's not necessarily all that humid there, but you have the ocean. You have the San Francisco Bay, and that acts as this reservoir of energy. As the heat evaporates, no, heat can't evaporate. As water evaporates, it absorbs energy and keeps things from getting too hot. Later, when the sun goes down, the cooler air, the moisture begins to condense. As it condenses, it releases energy and keeps the temperature from dropping too low. And so the temperature variations are not as large. Well, if there's heat, we could measure it, right? Chemists like to measure things. What we call the heat of vaporization is the amount of heat needed to vaporize 1 mole of liquid. Because if you're going to vaporize a mole of liquid or 2 moles of liquid, if you're going to boil a cup of water or 5 liters of water, it's going to take more energy to vaporize a larger quantity, right? So the heat of vaporization depends on the amount of liquid. For water at the boiling point, this number is 40.7 kilojoules per mole. So if we have liquid water going to the gas state, we have a heat of plus 40.7 kilojoules for 1 mole. That means we have to put this much energy into this system to get it to vaporize. Remember, the sign here is like the sign on money going into and out of your bank account. A plus sign means money's coming in. Plus sign here, energy coming in. Here's a negative sign. That's money leaving your checking account. This is energy leaving the chemical system. When water condenses from a gas to a liquid, it releases 40.7 kilojoules per mole of energy. It's negative because the heat is being given off. So we can use the heat of vaporization to calculate the amount of energy needed to vaporize a particular amount of liquid. It actually works as a conversion factor between moles of the liquid and the amount of heat needed to vaporize it. Here's a table from your textbook showing the heat of vaporization of some different liquids. So here's water at 40.7. Let's calculate the amount of heat in kilojoules needed to vaporize 2.58 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. This comes down to being a dimensional analysis problem. They're saying, well, you've got 2.58 kilograms of water. So I've got 2.58 kilograms of water. And what are they asking me for? Kilojoules of heat. So over here, I want kilojoules. How can I get from kilograms to kilojoules? I probably should have moved this over. Well, what other piece of information do we have? Kilojoules per mole. So if we had moles, then we could get to kilojoules. Using this as a conversion factor. How could we get from kilograms to moles? Grams to moles, right? We know how to do grams to moles, which makes me think grams to moles to grams, stoichiometry, right? Can we convert kilograms to grams? Yeah, we could do that. There's the path. If you get lost when doing problems like this, write the path down. If you don't want it showing on your paper, write it on a piece of scratch paper and burn it later. But write the stupid thing down. It makes everything easier. So now I just do my dimensional analysis thing. I have 3 arrows. I need 3 conversion factors. I'm going to stick the units in first and then figure out what numbers to put in and where to put them. So 2.58 kilograms times grams over kilograms, and then we're going to moles, and then to kilojoules. Kilograms to grams to moles to kilojoules. Kilograms to grams to moles to kilojoules. And then this unit comes down here because I want those to go away. They cancel out. Grams cancel, moles cancel. I've converted kilograms to kilojoules. I need numbers though. This is 40.7 kilojoules per mole. Write that vertically if the slash confuses you. 40.7 kilojoules per mole. So 40.7 goes on the top, and that's for every 1 mole of water. And you don't have to tackle these in order. Take the easy one first. So I thought that one was the easiest, and now I think this one's the next easiest. What does kilo mean? 1,000. It means 1,000. It means 10 to the 3. So I've got kilo down here. I want to put what it means on the other side of the line. Not that line. 10 to the 3rd. So that's the same as 1 times 10 to the 3rd. There's other ways to do that, but this is the one I showed you. And if you're struggling, just stick with this method. What's the relationship between grams and moles? It's the molar mass, right? So we need the formula for water, H2O, and then we calculate it using the periodic table. There are 2 hydrogens and 1 oxygen. And so the molar mass of water is 18.016. That's grams is equal to 1 mole. Another way to write that is 18.016 grams per mole. Okay? So I want 1 mole, 18.016 grams. Put it on the calculator. .58 times 1 EE3 divided by 18.016 times 40.7. Ooh, it's a big number. Is it wrong? No. Sometimes numbers are big. It's okay. This comes out to be 5,828 kilojoules. How many sig figs should I keep? Should keep 3. This one has 3, and that one has 3. This one's exact. This one actually had 4. I was a little sloppy. I'm going to keep this. So best thing is 5.83 times 10 to the 3rd kilojoules. Any questions? So let's do this one. This is a fun one. A drop of water weighing 0.48 grams condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only toward heating the metal, what is the final temperature in Celsius of the metal block? The specific heat capacity of aluminum is 0.903 joules per gram degree Celsius. My understanding is that they call these word problems now. When I was a kid, they were called story problems. And this isn't a very interesting story, but it is kind of a story, isn't it? It just goes on and on. Do not panic when you read a question like this. You just need to look at it, pull pieces apart, and make sense of it. Sometimes it helps to draw a picture. So I'm going to draw some pictures. So they're talking about a water drop, right? So here's my water drop. Now, it's kind of a funny looking water drop, but that's okay. What do I know about it? It has a mass of 0.48 grams. That's condensing. So that means it was in the gas state and it condensed on the metal, right? So I got my double gulp right here of Diet Dr. Pepper. I don't know if you can see, there's water condensed on the outside. Where did that come from? Is the cup leaking? No. There were ice cubes in here and it's cold. And so water from the air is condensing on the outside of the cup. So that's what we're talking about here. This water is condensing. It's making a drop that weighs 0.48 grams on this aluminum. There's energy involved in condensation. That's the heat of vaporization, because condensation is the opposite of vaporization. So when we have condensation of water, the heat of vaporization of water was 40.7 kilojoules per mole. We learned that 2 slides ago. So that's a piece of information. It wasn't given in the problem. You don't have to memorize that number. If you need it on a test, I'll give it to you. So it's condensing on the surface of a block of aluminum. Okay, so aluminum is kind of silvery colored. So here's our block of aluminum. I'll call him Al. What do we know about the block of aluminum? It weighs 55 grams. And it started out at a temperature of 55 degrees Celsius. I'm sorry, 25. I don't know where 55 came from. Oh, it's the mass. 55 grams. And its initial temperature was 25 degrees Celsius. What else are they telling us in this problem? The specific heat capacity. Do you remember the letter that we used for that? There's that Q equals MCAT. This is the C. So C for water is 0.903 joules per gram degrees Celsius. So now we have to think about what's happening here. It says, assume that the heat released, pointer, come on, there it is. Heat released during condensation goes only toward heating the metal. What's the final temperature? So we're trying to find the final temperature. As the water condenses, it gives off energy. And they're saying that all of that energy is going to go towards heating the aluminum block. Well, we had an equation for that, didn't we? Q equals MC delta T. So we know what the M is. We know what the C is. Delta T is related to what we're trying to find. How are we going to figure out how much heat there was? Well, we've got the mass of this drop of water, and we know how much heat it releases per mole as it condenses. So we're going to take 0.48 grams of water and figure out how many joules of heat. So I don't have enough room. So I make room. Let's do that more efficiently. You shouldn't be able to go off the slide, but you can. Pardon me? Maybe I could, I don't know. I'm having issues with aspect ratio and YouTube these days. Okay, I got sidetracked. Yeah, we're trying to figure out how much energy is released by that water droplet. So we've got 0.48 grams of water, and I'm going to choose joules as a unit because when I plug something into this equation, this has joules. Otherwise, I might choose kilojoules, but I'm going to use joules. So I've got this guy. This is kilojoules per mole. So if I converted grams to moles, I could use that to convert to kilojoules. So sad J. And then convert to joules. .48 grams, moles on top, grams on bottom. Kilojoules on top, moles on bottom. Joules on top, kilojoules on bottom. Well, here's our relationship between kilojoules and moles. 40.7. So 40.7 goes in here. Kilojoules and joules. That's like the kilogram-gram conversion we did. Kilo means 10 to the 3. So I put 10 to the 3 where the kilo is not. I'm not going to say 10 to the 3rd. Kilojoules is 1 joule. That's like saying 5,280 miles equals 1 foot. Is that correct? No. So there's that. And then for this, we need the molar mass of water. We just did that. 18.016. 0.48 divided by 18.016 times 40.7 times 1 EE3. And this gives me 1084. How many sig figs, if I was going to stop here, how many sig figs would this number have? 2. Because of this one. I want to keep 2 extras. So this number has 2 sig figs, but I'm going to keep the 8 and the 4 to avoid rounding errors. Calculator says 1084.36, blah, blah, blah. So that's joules. This is the amount of heat that was released by that water condensing. This is the amount of heat that goes into heating up the block. So this is equal to Q in our equation down there. I want to know what the final temperature is. If I calculate the change in temperature, then finding the final temperature would be relatively straightforward. So I want to rearrange this equation and get delta T by itself. So I'll divide by M and C. So M and C cancel out here. So delta T equals Q over MC. So we just figured out what Q was. 1084 joules. Down here, we've got the mass of the aluminum block, 55 grams. And we've got the specific heat capacity, 0.903 joules per gram. Yeah, that's a gram, degrees Celsius. The joules are going to cancel, the grams are going to cancel. I'm going to end up with degrees Celsius as my unit. 1084 divided by 55 divided by 0.903. 21.83. This should also have 2 sig figs. I'm just going to keep those 2 extras. That's the change in temperature. Did the block of metal get warmer or colder? Warmer. It's going towards heating the metal, right? So if this is the change, and that's the initial temperature, it must be 25 plus the 21.83. So T final equals the initial plus the change. So that's what, 47 degrees Celsius. Any questions? That's a challenging problem for 3A students. I wouldn't give you that as an exam problem. I think it's great to put stuff like that on worksheets, though, because it makes you think, makes you ask questions. Personally, I find problems like this fun. You know, it's a puzzle. We got to figure it out. What can we do here? What can we do there? How we can pull things together.